Imaging Science Fundamentals, what we call Fundamentals. It's a 100-level course that I teach for non-majors. So it's not for majors, which means that these students who take that particular course, the only requirement is algebra. And many of them have difficulty with algebra, or at least a few of them do. So what I'm going to be showing you is some of the things that I try to teach, and mostly, some of the analogies or visualizations that I show them in order to try to get them to understand these things. And then the second course is a graduate level course, some examples from that, more in my specialty area. So within imaging science, I do remote sensing in particular, so cameras on satellites and aircraft looking down at the Earth. So it's just some special things about that, but again, just some examples. And I'm not really going to be going through the math. I'll be showing you what math we use, I guess. Okay, so one of the things I start out of, the way I teach this course is that we teach a system. And so I actually start with the human visual system as a system. It's got components. It's a chain of processes that must occur for us to have this perception of visualization that we have. And so I break that down, and this is almost the outline of the course in some fashion. And so I'm going to go into each of those pieces, and I'll go through here now different pieces, different aspects of either vision or imaging with a camera, where we're going to start out with the source of light. We have to then form an image somehow, usually with a lens. Then it has to be detected, it has to be processed somehow, and then it has to be perceived or visualized. And so that fits, there's an analogy between the human visual system and an electronic system. So one of the first things I do is talking about how the photoreceptors, the rods and cones that are in the back of our retina, are distributed across the inside of the sphere of our eyeball. So we've got this on the left, upper left, we've got our basically angular distribution of where our light-sensitive cells are arranged around the back of our retina, and then translating that into a graph. So on this, I don't actually have it done, but this is basically visual angle across here. So 0 is in the middle. And then in terms of numbers of cells, which is going to tell us something about our acuity and our ability to sense, our sensitivity, it's given as the number of rods and cones per square millimeter. So this is something, these are things that I quiz students on. And in particular, this density is something that some of them do not get. They don't get the units. I usually ask them about the units, and they don't get the units right, often. So in one sense, the ability to take this visually and translate it into a graphical sense it's actually a piece of what's called spatial thinking, your ability to spatially translate something. So that's a problem area. And then we have our ability to see color. So in our retina, we have rods, which we use at night for nighttime visual sense. And then we have the cones during the daytime, which are our color-sensitive cells. And so humans are what's called trichromates. We see red, green, and blue. We have cells that are sensitive to red, green, and blue, and the combination of those allows us to see the full spectrum. Turns out that's exactly what happens in your camera. So in here, it's doing the same thing. It has red, green, and blue sensitivity, which is matched to the human visual system. And with that sensitivity, we can see color on a device like this. So I'll do more about the spectrum, but here I'm introducing this concept of the spectrum, the wavelength of the light, property of the light, and in this case, a relative response to light. So if it's higher up on the graph, it's more sensitive to that particular color. And so this concept, this is one of the concepts that I find the students have difficulty with, is what is a spectrum? Plotting a sensitivity of something as a function of distance or wavelength, wavelength in this case. That's a concept that is not, that's difficult to convey, and I think even graduates, some of my graduate students, in some ways, don't really think about and understand this. So then we're going on to, now we're passing on to image formation. So I kind of show, this is what happens with, do you have glasses or do you wear contacts or not? And what does that mean? What's happening in your eye? So I'll show this when I'm talking about human vision, but then I'll move on. Eventually I'm going to actually show, how do you know, how do you do lens formation? How does a lens focus light? But I'm just going to start with this viewpoint because they understand this, right? So I can say, it's the light, the lines, the light converges right at the back of the retina. That's in focus. If it's like me, and probably most of you, it's like that. And if you're farsighted, the hyperopic. So that then, this idea of focusing light leads to what's Snell's law. So it's Snell's law, which is this nice little trig equation here, which tells me how does light bend when it passes from one media into another media. So I have a light beam coming down here at a particular angle relative to the normal. And then I have, in this case, this is just like air and water. So I get a bending of the light. This equation describes those angles. And then I've got the pieces of this, N1 and N2, the indices of refraction. Then I have to define, right? So this is defined, it's equal to 1 for a vacuum, and all other indices are less than 1. So then I'll show some other examples of this refraction. One of them is what happens when light goes through a plate glass window from an angle. So what happens, light goes in, it's going to be refracted, so it's going to change direction, and then it's going to come out at exactly the original angle. And so then I tell them, look, if you're looking through a plate glass window from an angle, you're actually looking at virtual reality. Because everything in that you're seeing through that window is actually shifted over a little bit. You probably can't visually see it. It probably doesn't matter. But it's actually shifted over from where it really is. So that perspective. And then from there, you go to lenses. So then what is a lens? A lens is a piece of glass, which is then it's got a particular curvature, and you're trying to control, using Snell's law, where the light winds up going and focusing. And I will get back to lenses a little bit. So I already introduced the spectrum a little bit. So this is kind of my overview with a couple of things in here. Notice we've got this inverse relationship between wavelength and energy. And then I've got these equations here, the speed of light, frequency times wavelength. I can solve for frequency. I can calculate energy as a function which is directly proportional to frequency, which means it's going to be inversely proportional to wavelength. And I like the students to do some manipulations with these types of things. I have them in a quiz, like calculate the energy of this particular wavelength of light. And what I really want them to be doing is that they're going to be operating on these numbers that have these huge orders of magnitude range and trying to figure out, give them some sense of how does this all come together and to provide an answer. What I usually do in these is I will change when you look at the answer, I'll usually I'll pick wavelengths that have a very easy answer numerically. Like the answer is 5, something like that. But then I'll put all different sorts of magnitudes on the possible answers, like in a multiple choice question. So see if they can process through these types of things. And also the other thing is, which I often do, is the units. My quizzes have different units as possible answers. They all have 2 answers with 5, but one of them has the correct units and one doesn't. So can they think about the unit? Okay, here's one actually I want to. I actually have a GIF I've got from someplace. So I'll show them this when I try to describe waves. All right, so I've got an equation here, my equation for the wave, 2 pi, the frequency, and the time. And so this, I try to use these types of visualizations anywhere I can to try to explain, via some visualization, and we're going around the circles, how that makes out traces a wave. So now I've got an equation for a wave here. So I'm going to actually wind up using this a couple more times within the course. One of the first places where I use that is, and then I'm going to talk about, when I'm talking about waves and the wave nature of electromagnetic radiation, I'm going to talk about interference. And that actually becomes important in describing what's called the diffraction grating. So these are the 2 major ways that scientific equipment is going to spread out the spectrum so that we can measure the spectrum. And you can either use a prism, which is going to be actually using Snell's law, and variation of the index of refraction as a function of wavelength is why this spreads out for the different colors. And then a diffraction grating where you get a different pattern. Notice that the pattern is inverted, and like this, the blues and the reds here are opposite of there. And also that it does it symmetrically in this particular case. This is a grating. So what is a grating? A grating is usually, actually we have a laboratory where they're able to use them. In that case, it's a piece of plastic with lines drawn on it, parallel lines, very, very close together, very, very small lines. There'll be hundreds of lines per millimeter. So that's the grating. And that produces interference between the light waves. So what's happening there is essentially comes down to this. This is my equation that describes what is the angle at which I am going to get a particular wavelength of light, lambda, dispersed. So I can calculate where exactly that green light is going to wind up. And so the parts of this I've got, so the sine of the angle, this is the diffracted angle. And also this is a simple equation where I could have the more complicated case where, notice that the light here is impinging normally. It doesn't have to impinge normally. So there would be another factor in there. I could add in another factor for the incident angle. And so then I have my wavelength, G, which is the inverse of the number of, well, it's the grooves per millimeter is what it is. All right? So grooves, G is grooves per millimeter. And if I do the inverse of that, I've got what's the distance between grooves. So that winds up being critical. And then M actually is just an order number. Am I looking at 0, which is straight through, 1, first order? You get another rainbow with diffraction. I probably am not going to go through all of these things in this complicated with this particular class, but this is kind of what's going on. So I do show them though. Why is this happening? Why is there interference happening at these particular angles? And Anybody know? Can you visualize it? It's not an easy thing to visualize, by the way. And so what it is if I've got light going in one particular direction and I move off at an angle and I'm impinging upon a object at a certain distance, I've increased the path length. Every time I move over at another angle, I'm increasing the path length that ray must go. So if I move it over at a specific angle and I increase the path length by one wavelength for a particular color, that color will interfere constructively in that one particular direction. And all of the other colors at different wavelengths will interfere destructively at that particular direction, so I will get that color at that angle. And as I move, I'll get the rainbow spread out. Any questions about that? So it's path length difference.
Do you want to have a lens adjustable at angle then, so that you can get the best image? Is that
say that again. Say that again.
Do I want to have a lens adjustable at angle then, so that I can get the best image?
So maybe you're thinking about where the so this is not. There's no issue of focus here. It's where am I getting a particular color in a particular direction. So there are two things you can do in terms of building instruments. Is you take this grating and you actually twist the grating. And when you do that, you can make the colors move, right? So you make the colors move. And that's actually a device that it's called a scanning spectrometer. And then you just usually have a slit and then light, a light of a certain color is going through that slit, and then you twist it. And so you scan across all the different colors. That's one way to do it. In more modern instruments, most of the more modern instruments, what you simply do is right across this piece of the rainbow, you could think of it, is you put your digital detector across that. So one side of the detector is detecting red light and the other side is detecting blue light. It's as simple as that. So anyway, some interesting, it's one of my favorite pieces of combination of physics and imaging. The diffraction grating. Okay, and also the other piece of this I would say is that this is shown as transmission. It also, in many instruments, it's done as a mirror, actually a reflection, but still a mirror with lines drawn in. Okay, so then I also show Planck's law. So in physics, Planck's law. Because what I'm talking about really, I'm still talking about light and sources in particular. So here I want to talk about the sun. The sun is hot. Everybody knows, and I talk about that. What do hot things do? Well, they glow, right? And so the sun is really hot. It glows with light. So then I bring up this equation. Well, this equation describes the spectrum of light put out by the sun. I do use this. I show them. Here's a nice little applet that shows that you can actually adjust the temperature and you can adjust the wavelengths and the intensities so you can see what's the behavior of this equation kind of interactively. And then I'll go through all the parts of that, and yeah, it's an ugly looking equation, I'll tell them, but really it only has everything's constants except for T, which is the temperature, and then what's the wavelength you're calculating at. Everything else is a constant. Right? K, actually, this is a Boltzmann's constant, Planck constant, speed of light, and then you have another wavelength in there. I'll also bring up the units. So I've got watts per meter squared per wavelength interval, just as bringing up a unit. And that's going to give me, across the spectrum, it's going to give me a curve that describes the intensity. And I can do that for sunlight, and they'll put in the temperature of the sun, and they'll see a curve that's peaking in the visible part of the spectrum where sunlight peaks. Change the equation to the temperature of a fire, I've done some research on fire, and we know we can see fire, right? It's kind of orangish color, yellow-orange. Well, you don't have any blue light put out by a fire, but you've got a little bit because the peak, where this peak, the peak in a fire actually shifts towards the infrared radiation, and there's a little tail of going into the red and the yellow, which produces the color that we see in a fire. And then we go to something like the temperature of an oven, right? You know your oven's hot. You look inside. Well, the paint, it doesn't look any different than when it's cold, right? It's because it's all emitting infrared radiation. So I give those types of examples to try to explain. This equation is describing those examples that you can kind of understand. When I do go to that, I talk about the Planck's equation, and I will also have, by this time, talked a little bit about absorption, and I'll talk about visible radiation and thermal radiation, those types of things. But once I kind of get all the pieces of that together, then I talk about the greenhouse effect. So this actually, there's a bunch of things that come in here, and this one graph here actually describes, this is the greenhouse effect. Why do we have it, and why do CO2 and methane impact climate? So most of the radiation that's coming down is from the sun, and this is normalized. It's actually one that spectral intensity is normalized. Most of the sunlight is in the visible part of the spectrum. The atmosphere is clear, so the sun is reaching the ground. Kind of all goes together. That's why we see in the visible. Our ability to perceive, imaging is peak to the peak of the sun spectrum. And that's where we have our sensitivity. And then all these little dips here are from, the atmosphere coming in and removing, absorbing some of that radiation. And this comes from the gases that are in the atmosphere. In this particular case, most of what's happening here is from water vapor, or oxygen, or ozone down at this end in the ultraviolet. And what does this sun do, or sunlight striking the ground, heats up our ground, heats up the surface of the earth. But remember, I went back to that Planck equation. I said, when it's at a temperature of ground temperature or something like that, all the radiation is emitted in the infrared. It's not emitted in the visible anymore. It might be reflected, but it's not emitted in the visible. And then that emission, then, which is the curves here, these are my Planck curves, has to get back up through the atmosphere. Except now, the atmosphere is absorbing, and only about 15 to 30% of it gets back up to space. So it's trapped. That's the greenhouse effect. Radiation is coming in the visible, heats up the ground, it tries to escape back to space, it's emitted according to the Planck equation, but then it's absorbed by the atmosphere. So we have the greenhouse effect. So you add more carbon dioxide and methane, which absorb here. You add more of it, it's going to absorb more light and warm up more. Okay, so then just kind of moving on to different areas. And this is where I said we're going to come back to lenses. I start with pinholes, and this actually is similar triangles. Pinhole is nothing but similar triangles. A pinhole, very small hole. We have light here. There are only very specific directions that, the light from the hand can only go in that direction through the pinhole. So it's going to wind up here. From the nose, it's only going to there. It's going to wind up there. So you can form a pinhole image. Right? So they do this in a laboratory setting. Actually work with this. So the idea is working with similar triangles, the size of the object and the size of the image, you should be able to calculate those. You do an experiment, and of course you move the pinhole at different positions, and you change those similar triangles, and you change the size of the image. All right? So they seem to do pretty well with that in the laboratory, but when I quiz them, And I just present this to them. And then I say, move the pinhole closer to the image. Does the image get smaller or bigger? And they don't necessarily, they may have a hard time with the similar triangles. I'm sure you're all well aware of some of these issues. Okay, so then the pinhole then leads to why do we not have pinhole cameras? The main reason why is that not enough light gets in. The pinhole's so small, the image that's being produced is not bright. So we have lenses instead. But that means that, what does that mean? That means we can make this a much larger aperture instead of a pinhole. It's bigger, but we now have to somehow control the light and focus it. And that's what our lens does for us. In fact, when they're doing their experiments with pinholes, I have them do different sizes of pinholes, and what they see is when you use a bigger pinhole, it gets blurrier. You know, it's a really tiny one, and then a little bit bigger, the image gets blurry. And so again, it's the idea of the similar triangle. The angles are different. So then they go through a second laboratory where they're basically dealing with this. They have whatever their object is. They have to measure the two distances, Z1 and Z2. And actually, so this is what they wind up measuring, and then they have to calculate F. So they want to determine the focal length of the lens. I just give them a lens, do this experiment, tell me what the focal length is. And so in doing that, I have them one thing is I show them as they're going through the process that this is highly nonlinear, for one thing. It's not a linear equation, very nonlinear, the way this behaves. The size of the image, the size of the image. So, I asked them to look at, even though it behaves nonlinear, it does behave consistently. So as they move it, it should, like if it's getting smaller, it should continue to get smaller, and not suddenly jump back up again or something like that. That's a problem, right? So that's one way that I can kind of check on that they're doing things correctly. So there's just the equation for a thin lens, and then there's this part, which this is more the visualization part, so not so much mathematics, but you can visualize where you're going to have your image formed. This is essentially, working with your equation. You still have the parts of your equation, but graphically you can actually determine where that will be instead of calculating it. So the lens is in the middle here. So it's a focal length for a lens. And the focal length, you can think of it as the focal length on either side. So this is how you do this. And you only need to draw two lines. So there's the collimated ray and what's called the chief ray. And that will tell you, this is my object. I've got an arrow here with a peak there. That's that particular size. I draw a parallel ray, and a parallel ray to a lens will be bent to go through the focal point. So it goes there, and it goes to the focal point. And in fact, I can draw that line once because it's never going to change. No matter where I take this object and move it closer or move it farther away, that doesn't change. What does change is what's called the chief ray, is from some point on this through the very center of the lens. And if it's going through the center of the lens, the lens is parallel there, and there's no bending, right? It's going to wind up going straight through. And so that, my line is just going straight through. Where they intersect is where the image is formed. So I can figure out Z2 distance and the height of the image from this. So I can graphically do that. And it's just going through the lens equation. And let's say just to kind of further this in this graphical sense, there are actually 7 cases. Depending on mostly it's based on related to how far is it from the focal length or from the lens. There are 7 special cases. Anything else is just a subset of those. So when it's at infinity, when it's greater than twice the focal length, when it's between twice and the focal length, when it's at the focal length, when it's inside here, and then it's when it's right at the lens. Those are our 7 cases. There is a special case. Again, graphically, I'm not sure mathematically how interesting this is. I guess it becomes, it should be, you should be able to go through the lens equation. When the object is closer than the focal length, which means like this tip of the arrow is, say, right in here, right underneath the D and collimated. Notice that that ray is going like this. And in comparison to the collimated ray, those are actually deviating. Right? They're not coming to a focus. Except they do if you backtrack, and they come to a focus back here. And so, okay, so they come to, or those lines would intersect back here someplace. And notice that then I would have my arrow right here, very big, and on the same side of the lens as the object, which is what's called a virtual image. You can see it, but it's not a real image. It's not an image you can project on a plane and capture it. So the example of what that is a magnifying glass. You move the magnifying glass very close to something, it gets bigger. It's also upright, it's not inverted. And you could potentially take a picture of it, but you can't capture the image itself. It's a virtual image. All right, moving on, continuing with cameras, here's another thing I like to do. Here's actually brings back to a little bit of math, is, and this is becoming less interesting now because people don't have cameras anymore, right? They have things that you just press a button. But when you had a camera and you had f-stops on it, what do those numbers mean? So I think probably to most of you, these numbers are familiar. These are stops on the camera. Well, what do they mean? So it goes back to defining an f number as the focal length of the lens divided by the diameter of the lens here. And the intensity of light that is able to come through that circle is dependent upon, there's a square relationship. And so I wind up getting this curve as a function for that as you open up and close the aperture. And then this is just showing specific ratios for the f number, specific f numbers, ratios of f to d. You get a change in intensity of a factor of 2. And that's what the f-stops are. So the idea here for a photographer was, let's say they look through their camera, they're seeing the exposure, they're at an f-stop of 8. If it's too dark, they go click once, and they have twice as much light. They go click twice, they have 4 times as much light. And that's why these specific f-stops, because it's factors of 2 in the amount of light that's let into the system. So I kind of like that one. It's pretty mathematical. Going to detector systems. So this would be, I do talk about I kind of just very briefly discuss the response of film to intensity. We don't have film cameras anymore, so we talk about digital detectors. And talk about, as I get exposure, more light, how does that digital response change? And then I can just look at the way this curve responds. I've got a dark current, so I've got some signal. So I've got I've got some signal in the absence of light. I've got a linear proportion. As the light goes double, my digital counts go double. So I've got a nice linear equation for this with an offset, which is a certain signal that exists even in the absence of light. So it's got an intercept, and then there'll be a saturation point. Digital. Any detector can only measure so much light. At that point, then I kind of move on to this is actually color. This would be like a microscopic view of the front face of the detector in your cell phone camera. And what it's showing is you see red red, green, and blue filters, light filters, on top of each individual pixel. That's how a color camera works. In film, it used to be layers, right? 3 layers of red, green, and blue sensitive dyes. And now we've gone the other direction spatially. Instead of layers, it's side by side. So which means, when you think about that pixel right there on your image, it's only detecting blue light, right? So how do you get a color version there? Well, you have to interpolate. You interpolate the pixels that are around that to determine. So if I got my blue measurement, but I'm going to interpolate these 4 green pixels to estimate what the green would be there, and I'm going to interpolate these 4 red ones to estimate what the red would be there. Now I have a blue, a red, and a green value, and I can get a color from it, right? But it's interpolation. It's interpolation in a local area, what we call a kernel, and it actually winds up leading to things like this, which actually is not particularly important in the photos you're posting on Facebook. So what am I doing here? This is my scene. My scene is going to consist of black and the edge, and then actually here's the rest of the scene, which is white. I've got a solid, a very straight edge, something black to white. And then I'm looking at the scale of the pixels. I'm not thinking of a photograph. I'm actually looking in and zeroing in on the pixels. So this is what I would like it to do, but that's not what actually it detects. What it actually detects is something like this because of the interpolation across that. All right? Does that make sense? So I have to interpolate. And then when I interpolate, when I do that neighborhood interpolation, it actually depends what's the order. Are these the blues right there and there, or is it the reds that are right there? Between those, I'll produce different colors on an edge, a black and white edge. And then I actually show them a photograph. I've got an aerial photograph. It's got something that's basically has a white roof and then a very, very dark shadow. So it provides essentially, this black-white edge. And I zoom in all the way to you can see the pixels, and I show them these colors exist on that edge, depending on what's the relative relationship of the edge to the way the pixels are distributed.
And yet they don't really exist.
Well, normally, we don't see the pixels because we have so many pixels in our image, we don't see them. We actually, when we look at the image, we're just going to see a black and white edge. If we zoom in, we can see this. It's there, right? So it's our inability, our eyes cannot see the pixels. And we build cameras so that we cannot see the pixels, of course. Okay, so then that leads to sampling and quantization, important things. So the concept of sampling, spatial sampling, dividing the scene into discrete spatial elements, which is our pixel, right? So this is what the scene actually looks like. It's projected with my lens, actually on the back of the camera looks like that. But in my camera, I have this grid, which is the pixels. I've got these little square, micrometer-sized pixels in the back of my camera, and so then they sample that. They take this continuous image, and it becomes a digital image. Right? So it's sampled in that way. So you get this. So that's sampling. And then once you sample, then you're going to quantize. So that's the actual measurement. You're going to count how many electrons are there, and they're going to turn that into a digital number through an analog to digital converter somehow. And so then we have a representation. The typical representation is bright is a higher number, and black is a lower number. So actually, in this, the way I've got this scene, this should be wrong. These outside pixels should be black because they would all be zeros. And then the center pixel, which is the brightest one, would be like the highest number, 150. So I'm going to quantize. So that's just the concepts of sampling and quantization in a digital image. But more importantly, maybe with the quantization is this. Here's a really nice, I think, a beautiful visualization of, you get to talk about you know, bits. And what does that mean? You've got if you only have one bit of you sample or you quantize, and you're only quantizing to one bit, you have a 0 and a 1, your possibilities are black or white. And your image can only be black and white. But if you add more bits, you know, 2 bits, suddenly you have 4, right? Black, white, and 2 grays intermediate. You go all the way down to 8-bit, and essentially for this, to us, this looks continuous. And so this use of 8 bits in this guy is based on the human visual system response to the fact that we see this as being continuous. And if you look at this slide in good quality, especially in 64, even now I can see actually some gradation here, or I mean the individual pieces. And even in 128, you'd probably see, if you looked really closely, but once you get to this, you don't see it anymore. So a commercial camera, a consumer camera, is going to at least have 8 bits. It's going to quantize to 8 bits. Right? If we don't do that, you see all sorts of artifacts in your images. Okay, so the next thing I do is I just show images at each of those quantization levels as a nice example. And of course, the 8-bit one looks like a black and white photograph. And in fact, film was the same thing. Film provided essentially 8 bits of resolution. And then from there, we can start to talk about like file sizes. I'm gonna sample, so I'm gonna create a certain number of pixels, and then for each one of those pixels, I have to measure it to a particular bit depth. And so then I can start to think about what does that convert to file size. So this would be just straight up, I've got a certain number of pixels, this is 100 by 100, and it's 8 bits. If I can do the calculations, it's going to take this much, basically computer space to store that image. Right? That's what I have to do. This little bit about approximately, and here's just that in digital terms, this is not exactly 1,000. Right? That's why I've got the approximate here. Okay, so that's some of the spatial stuff, sampling and quantization. And then there's, this actually is leading into, what I'm starting here is Fourier transforms. In this class, I talk about Fourier transforms. Okay? So, this is actually, at the graduate level in particular, this is what imaging science is. One of the fundamental pieces of imaging science is how to do two-dimensional, or understanding an image through using Fourier math, because you can do it in 2 dimensions, and that you're basically understanding the pattern of light and dark across an image. And one way to do that is to do a Fourier transform of it. So I kind of introduce that, and I just tell them this is what imaging scientists, this is a key tool, mathematical tool for imaging scientists. But the idea here being, if you take a line of pixel values across this image, this particular simple cartoon, what you get is a dark, a light, a dark, a light. But remember, so this is going to be my pixel intensity, my brightness. And then across here now, I've got spatial distance. Previously, I'd introduced waves, but I'd done it in time. Now I'm going to do it spatially. You could think of sort of as a spatial wave. And so I've got the distance. This is basically my wavelength. All right, that's going to wind up being my wavelength. This is digital in an image. And then I just go through this to introduce what does a Fourier transform do, or what is it, Fourier series. What does a Fourier series do for you? And then remember, I've already introduced the wave. Now it's spatial instead of wavelength, or instead of time. It's spatial instead of in time, something like that. And so I've got this square pattern. And so that's a very simplest, right? It's the simplest pattern you could think of. And I can approximate it with a wave, but I can do a better approximation if I add in another frequency, another wave at a different frequency, a very specific frequency. Right? So I've got a very specific frequency here, and I do even better here with this one. And I start to approximate that pattern. And so if I do a Fourier series or make this in 2 dimensions of an image, I describe the pattern of bright and dark across an image. I can do it mathematically. What I will do personally is I will do this, I will actually draw this on the board to show them. I'll actually draw it to try to get to them. And so they see it as it traces out. I start to approximate that square wave better. Okay, so then where does that lead? Eventually that leads into, everybody knows JPEG, right? As an image. Well, why does JPEG even exist as a file type? It's all about compression. It's to take the file size that you need to store in order to convey the information, to reduce it. There's actually, unless, if we had infinite computing storage capacity, there would be no reason for JPEG. You do not need it. But the only reason it exists is to reduce the storage. So now I've got this example. This shows basically half of JPEG. This is the spatial component of what JPEG does. When you take an image and your camera is actually processing it, right, and is putting into that JPEG format and storing it, this kind of shows what it's doing, part of what it's doing. So if you've ever noticed in your JPEG images, you can wind up having these blocky things. These are 8 by 8 blocks, pixels, 8 by 8 blocks of pixels. And basically now I've got these patterns, like I showed with the Fourier, in the 2 dimensions. Right? These patterns, and they get more complicated as they get down to this corner, right? They get down to this corner, and it's basically every other pixel is a different bright and dark. And the combination of all of these, you would think, can produce essentially, like that Fourier example, any arbitrary pattern. That's the idea behind JPEG, right? So then what do you do with that? Well, if your particular pattern does not have this frequency in it, you don't need it. You throw it out. And that's the act of compression, is removing the information that you don't need to store in order to reproduce a particular pattern. So I can show you an example of that. This is a beautiful, I think, visualization. So what this is showing, this will just keep running through so I can describe it here. The left is the image that's being created. So it started from that pattern across that spatial thing. And it actually goes in kind of a diagonal. It starts in the upper left corner, which was just white, uniform, and then it kind of does diagonal pattern back and forth. And as it's doing that, it's getting more and more complicated. Until it gets down to the lower right corner. That was the most complicated. So this is the pattern that's being created by summing those up. So here I've got the pattern. This is the pattern within that that I'm operating on. And then the number represents, am I using much of that pattern, or is it an important pattern or not an important pattern? It can be, it's going to range between -1 and 1. And if it's near 0, it's not important. It's not important. And whenever you see that this number is quite close to 0, the center image is black, so it's adding nothing. All right? So anytime the image is very, very black, it means you can throw it out. And a lot of these images are black, and just a few of them are particularly bright. And that's JPEG compression, at least the spatial piece of it. right? And in the end, you can form this quite arbitrary, letter A by just summing up those pixels, right? There's a little bit of blurring across here. That's okay. Right? Any questions about? Let's see, how much time do I have?
Or over.
Oh, okay.
Yeah.
All right. So I think that's for 4 over. Then I think we're good.